In the previous lecture, we had been talking about convexity and then about like conditions to check convexity. So those are actually more handy than the definition of convexity. Then as an immediate consequence, we had Jensen's inequality for convex functions. And I had mentioned that that is pretty much of like a tautology, meaning like it just follows from the definition. The real crux of the matter there is that we have conditions to check for convexity of functions based on the second order derivatives. Looking at the Hessian, if it is positive definite, for example, we know that the function is convex, hence Jensen's inequality holds. And based on this criteria, based on which we can figure out whether a function is convex or not, helps us to get these inequalities. And then we figured out a few useful inequalities, like AMGM was a consequence of Jensen's inequality. And then based on that, we proved Holder's inequality. And again, as a consequence of Holder's inequality, we proved Minkowski's inequality, which essentially showed this function from Rn to R given by, so if you have a n vector, so LP norm of this vector is given by, you add all these coordinates, take to the power p and add all these coordinates and take to the 1 over p. And what I had mentioned was, first of all, note there are three important cases. One of them is L1 norm, for example, is just summing this up. Summation I equals 1 to n xi. If I am looking at the L2 norm, then essentially I'm looking at this quantity, which is more familiar. It's a Euclidean norm, like the unit ball, for example, is just a sphere. And then the third important case is the L infinity. If you take limit of p going to infinity, in a sense, you'll get max of absolute value x1 all the way up to absolute value xn. So typically when we have a norm, essentially a norm is a way of measuring size of a vector, way of measuring size of a vector. So when we're trying to solve certain problems, like for example, standard problem that we have in the back of our mind is linear regression, for example. We have all these data points and we want to fit the best possible line. So you have xi here and the value yi's are given to you. So x1, y1, and so on. And you want to fit a line to this, xn, yn. So essentially what you ideally want is yi should be equal to beta naught plus beta 1 xi. So this is the intercept term, this is the slope term. So this should be true for all I between 1 and n. But that is not going to be the case in general because there will be some error terms. So you'll have an epsilon I, which is denoting the error terms. But in some sense, you want to find the beta naught, beta 1. So essentially you want to find the line which has the best fit. So typically in linear regression, you will try to minimize this quantity. 1 equals I equals 1 to n, minimize over beta naught, beta 1. These are in fact just numbers. Beta naught is in R and beta 1 is in R. You want to do this. Okay. Or so, but the thing is, like I said, this can be a bit arbitrary. Why take squares? You could also like essentially this is saying that this minimizing quantity is 0 if and only if yi equals beta naught plus beta 1 xi. They're all 0, which means yi is equal to beta naught plus beta 1 xi. So essentially it's trying to express the fact that the errors are small. But the measure of being small is essentially depends on what norm you choose. That is a way of measuring size of a vector. Here the vector is essentially y1 minus beta naught minus beta x1 and so on, yn. And you want to make this vector small. Individually, each of these entries in this vector you want to make small. So the norm should be small. But depending on what norm you choose, for example, you could have chosen to do this. Then this becomes somewhat of a linear programming problem. So if I take absolute value, yi minus beta naught minus beta 1 xi and minimize over beta naught beta 1, and here there is no constraint. For example, it is the decision space is the whole of R2. If I take beta naught beta 1 as an ordered pair, that is in the whole of R2, and I guess you don't want it to be a vertical line, so maybe you can put some restrictions such as the slope is not infinity or something like that. You're not allowed a vertical line. Yeah, but in any case, so this is becomes more like a linear programming problem. Or you could go further and say, I want to minimize the maximum of all these. So all of them correspond to saying that I want each of these individual entries to be quite small. The error term should be small. Okay, so maximum of this yi minus beta 1 xi. All right. So So yeah, so in this context, it depends on what type of problem you're solving. Maybe squares denote certain type of energy. Amplitude square is like energy. So maybe if you have a certain type of problem where square is more natural, those are the error terms you use. But maybe there's a different problem where you have to use a different sort of norm. So that's why knowing and norm, since it is a way of measuring size of a vector, it better satisfy the triangle inequality, and it also better satisfy the fact that norm of lambda times x, meaning if you scale it, the size of the vector is scaled by that absolute value of lambda. So those were the two defining conditions for a norm, and norm became a convex function from Rn to R. And then, but after we defined it this way, we actually proved that this is a norm by using Jensen's inequality. So here we just wrote an expression, look like a plausible expression for measuring size of vectors, but we still have to prove that this is actually a norm. And that's exactly what we did using Holder's inequality and then as a consequence, Minkowski's inequality. And here I want to tell you again something from statistics which may be familiar to you. Forget about linear regression. Let's say I have these data points x1 through xn, and I want to measure like some central measures, central tendency or something like that. So you know mean, median, mode, right? So what is mean? So mean is equal to mean of this data set is x1 plus xn over n. So if I call this equals y, if mean is y, it is actually solving a certain optimization problem. What is that optimization problem? I want to approximate all of these numbers by one number, which will be a representative of all these numbers. So I want to find a number. So I want to minimize this quantity, x1 minus y squared. So find y in R, xi minus y squared, I equals 1 to n. If you minimize this quantity, so minimum of this is in fact is equal to, okay, so the argmin of this, I should say. So you want to minimize this quantity. This is a measure of central tendency. So you want to find a y such that the difference between all these data points is quite small. So it turns out argmin, that means the particular y which causes this. So argmin of this is in fact equal to the mean that is familiar to you. Now, if you replace this square by a 1, of course, I can always have written it as a like an L2 norm kind of thing. But anyway, the square root doesn't matter when I'm trying to minimize. So if as a measure of central tendency, I'm using L2 norm, then whatever I get is the best approximating number is this mean. If I use L1 norm, so maybe you can think about this. So minimum of, so let's say argmin of this, if I'm talking about xi minus y, I equals 1 to n. So I'm not, instead of taking square, I'm taking L1 norm. So then this argmin is equal to actually the median. So this is something you can think about. It's actually not very hard to prove. You can just play around with 2 numbers, 3 numbers, and you'll notice that this is actually the median. And if you go for L0, then it will be the mode. L0 is essentially L0 norm, although it doesn't really fit into this picture, because in this picture, you always assume P is bigger than or equal to 1. And P equals infinity was a definition, because it's not really clear how to say xi to the infinity and then do a 1 over infinity. So here, this is to be interpreted as the limit of this thing as P goes to infinity. Okay. But L0 norm is essentially caring about, if you pretend, so this is not in that class. So remember that there P is bigger than or equal to 1, but you can define something like an L0 norm by pretending this quantity makes sense. And xi to the 0 is 1 if xi is not equal to 0, and 0 if xi equals 0. So L0 norm is essentially measuring how many of the vectors are 0 or non-zero. So yeah, so how many vectors are 0 or non-zero? So it doesn't care what the actual value is. It essentially cares about how many of these are 0 or non-zero. So L0 norm will always return an integer, and it will in fact be a norm. It will not be a norm. It will be like, it will satisfy triangle inequality. But of course, when you do lambda times x, that scaling factor, it will not satisfy. So maybe I'll put in this L0 norm. So sometimes you just care whether something is 0 or not. And this plays a big assumption in signal processing and so on, because this talks about sparsity. Sparsity assumptions means I have a big matrix. I want to kind of reconstruct it based on my data, but I may not know, like if it's a very high dimensional data, of course, I'm out of luck. I may not be able to retrieve every entry in the matrix. But sometimes if there is assumption of sparsity, meaning if I tell you that 80% of the matrix is full of zeros, or in this L0 norm kind of statement, it's just saying that L0 norm is quite small. Uh, so in those type of assumptions, many algorithms can be developed. So this is also a pretty standard thing people think about. Now with this definition, if I talk about argmin omega y in R, xi minus y, L0 norm, meaning it just cares about how many of these match are zero, meaning how many of these uh, are equal. So for which y, maximum, minimum number of values are xi. Okay, perhaps here I should put an argmax. So in that case, what you get is the mode. Mode is essentially whichever values are repeated the most, those values you take as so that is the value you use as your measure, like as your approximation for all of these xi's, whatever value occurs the most. So all of these measures that you have seen in statistics can be interpreted in this sense, looking at some LP norm and trying to figure out what is the closest number in that norm. All right, so I hope this motivates you to think about like optimization. So these are not just some random examples that are coming up. Like entropy also shows up when you're talking about comparing probability distributions. Here you're talking about distance between vectors. So sometimes what might happen is you want to find the best possible probability distribution, and then you want a distance function between distributions. And there is something known as the Kullback-Leibler divergence, which uses the entropy that I had talked about, the x log x type of term. So that's a, so all of these are examples of convex functions, right? And I have told you that like the theory of optimization, a lot of the techniques that we have developed, or at least the qualitative techniques that we have, or ideas that we have developed for linear programming, can be pushed forward in this case. And now we have a like rich class of examples which show up in the real world very often. So essentially we're not studying something very specialized and something maybe perhaps not very useful. That's not the case. That's what I'm trying to convince you here. All right, so let's go back to the mathematics now. Yeah, and so far we have just been like trying to understand convex functions in general, and we'll be continuing to do so in today's class. Next class onwards, we'll actually hit like optimization proper, meaning we'll talk about Lagrange duality and look back into our motivation for studying duality, which was like finding lower bounds, like ad hoc lower bounds and so on. So based on the same ideas that we had for duality in the simplex method, remember, like we had three motivations for duality. First of them was finding ad hoc lower bounds for the optimal solution. And somehow it turned out the ad hoc thing by strong duality theorem actually turned out to be the optimal value by strong duality. Then we had two other things where there was the verification certificate needed and so on. So that for that we'll need some extra conditions on our optimization problem. But in general, condition one will always be true. Weak duality will always be true. So with this in mind, we're trying to understand convex functions as well as possible. And the reason I mention it might feel like we're doing just a string of theorems, but none of these theorems I have tried to optimize the number of theorems we say. So optimizing quote unquote, in the sense. So to draw an analogy, you may have heard of something known as Chekhov's gun. So Anton Chekhov, he was a Russian playwright. So his principle is that if in the beginning of a play or a movie, if I see a rifle, then that rifle must be fired by the end of the movie. And in principle, essentially what it means is do not introduce something which is extraneous, like just for the heck of it. Otherwise, the audience loses interest. They throughout the movie, they're thinking that, okay, maybe this plays a role in that movie, but it looks like if it doesn't, then it's a bad play. So the Chekhov's gun is that concept. And here also we'll be trying to adhere to that. So even if you feel that some of the definitions are just, it's like a series of definitions, that's not the case. We will actually be revisiting it at some point in the future lectures. So don't zone out. That's my point. All right, so we'll essentially start the new content of today's lecture, operations that preserve convexity. So we're still trying to understand convex functions, and we're trying to build new convex functions. We saw some examples, but how do we build um, new convex functions from old convex functions? All right, so operations that preserve convexity, or in other words, we are trying to build new convex functions from old. All right. So one typical way, what we have seen is, first of all, one is taking arbitrary suprema of convex functions is again convex. So that's a way of building new convex from old. And in fact, I mentioned that affine functions are convex. So I can build newer convex functions by just taking suprema of affine functions. So that is the recipe I'm talking about. You have some very familiar convex functions. Then how do I construct new ones? All right. So non-negative weighted sums. So if f is convex on some domain omega and I have alpha bigger than equal to 0, then alpha f is convex. So this is clear. Like if you are looking at Jensen's inequality, of course, alpha f will satisfy. It's just a matter of multiplying alpha on both sides. So if f is convex and alpha is bigger than equal to 0, then alpha f is convex. And if it is less than equal to 0, then it is concave. Because by definition, f is concave if minus f is convex. All right. And another thing is if f1, f2 are convex on omega, you could have taken f1 to be convex on omega 1, f2 to be convex on omega 2. Then you would say f1 plus f2 is convex on omega 1 intersection omega 2, because to be defined, it has to be defined on wherever this is defined, intersection wherever f2 is defined. So f1 plus f2 is going to be convex. So combining these two facts, what we have is, if I have, so is convex if alpha I is bigger than equal to 0 and f1, f2, fk are convex on omega. Or you could have taken omega 1, omega 2, omega k, then this function will be defined at first on the intersection of the domains, and that's where it will be convex. So by taking non-negative weighted sums of convex functions, you can build up new convex functions. All right. And the second way is composition with an affine mapping. All right. So now if f is a map from Rn to R, if this is convex, so defined on all of Rn, and A is some matrix from Rn cross M, and B is some vector in Rn, then this function g from Rm to R, so defined as a composition. So A is actually a function from Rm to Rn, right? Right. So G defined as g of x is equal to f of x ax plus b. So A is a function from Rm to Rn. So Ax will be a vector. So for all x in Rm, it will be a vector in Rn, Ax, and B is a vector in Rn. So Ax plus B is a vector in Rn. So this quantity is well defined and takes values in R. So g of x, if you define it in this manner, then G is convex on Rm. So this is also something you can check directly using Jensen's inequality. The fact that this is affine, it will not only satisfy inequality, but it will actually satisfy equality. So if I take convex combination of x and y, then A of that z will be equal to lambda ax plus b plus 1 minus lambda ay plus b. Sorry, az plus b will be like that. So that b term is the offset term. So because equality holds, and so overall the Jensen's inequality holds, so composition with an affine mapping will still give you a convex function, but it is not true that if you compose two convex functions that you will get a convex function. So you can try to think of a counterexample, and in fact you can find smooth counterexamples also, because convexity is all about looking at the Hessian, and then you use, so it is all about taking double derivatives, so then you use chain rule and so on for composition of functions, and then find conditions on these functions f and g, such that the composition is no longer convex, whose Hessian is no longer positive definite. So that's something you can play around with. And 3 is what I mentioned at the beginning. It's pointwise maxima and supremum. So pointwise maximum and supremum. So meaning f of x is equal to max of f1x. So f of x is max of these numbers, fkx. And f1, f2, fk are convex on omega. If these are all convex function, maximum will also be convex. All right, so this will be left as an exercise, how to prove it. Yeah, I mean, it's just a matter of checking Jensen's inequality. So with this definition, you just have to check that for f of lambda x plus 1 minus lambda y is always going to be less than or equal to lambda fx. And then use this definition. All right. So pointwise maximum and supremum. So what is the difference between maximum and supremum? So typically, if you have finitely many numbers, you talk about maximum because maximum is really attained. So supremum would be if you have an infinite family of convex sets, then in fact, the supremum may not be attained by any of these functions, but it is a real number. It's still some sort of real number as long as it is bounded. So you assign that value to f of x. So the pointwise supremum is also going to be a convex function. All right. So here's a quick example which might look familiar. So we had seen the order statistic, like given a vector, if I isolate, like, let's say the biggest one, that itself is a convex function. That assignment of the biggest vector, the max of x1, x2, xn, because of this. So the function x goes to the first coordinate is a convex function. You can check that. It's an affine function, right? And x goes to xn. Each of them is a convex function. So maximum of all of these is again a convex function. So the order statistic will lead to convex functions. And here for x belongs to Rn, let's define x of I as the ith largest component of x. Component of x, so that you have x of 1 is bigger than or equal to, so that's the biggest element, and x of n is the smallest of the coordinates of x. So now let us define f of x to be summation I equals 1 to r xi, meaning you take the r largest entries and you add them up. So this is the sum of the r largest elements. Elements of x. Then actually I can rewrite this as, so maximum of these numbers xi1 up to xir says that 1 less than equal. So I1 through ir just are the indices, are indices. So if I take this sum and I maximize this, of course it will be maximized when I take the top r elements, then it will be maximized. But each of these are convex functions, right? If I have this chosen I indices I1 through IR for any fixed choice of indices, this function is going to be a convex function. So the maximum is also going to be a convex function. Hence, this proves that this quantity is actually a convex function. So this is what? So maximum of all possible sums of r different components of the vector x. So that is about n factorial over n r factorial n minus r. So just n choose r. That many elements at max in here. So you have finitely many things. So it is in fact the maximum. All right. And of course, you will notice that when you are maximizing this, even if your original functions are all smooth and nice, but this max will not be nice. But still, the fact that it is not smooth does not mean it is not nice. It is still convex. So we still have a reason to call it nice. So, and in dealing with problems like these operations, like maximum of two functions, minimum, they arise naturally. So one should not feel stuck in a bind. For example, if it is smooth, you know that, okay, I'll take grad f equals 0. I have all these methods from differential calculus, multivariable calculus to minimize or maximize a function to find local minima. But now that I have a max of two functions, I don't have the fact that these are smooth anymore. But in the case of convexity, that's not a problem. Like the max is again a convex function, and if you have techniques to deal with convex functions in general, so these will be some things that do not strike fear in your heart. They're still something that you can work with. All right. Now, actually, we said we will build up new convex functions from old, but it turns out this number 3 is in fact a universal recipe to build convex functions. out of affine functions. So in fact, so this is a theorem we're going to talk about. So representation of convex functions as pointwise supremum of affine functions. So affine functions, naturally you understand these are convex functions. So in fact, they're both convex and concave, because they don't not only satisfy Jensen's inequality, but this also satisfies negation. The inequality can be replaced with its equality. So those are convex functions. And we saw this operation of max also gives you convex functions, but it turns out every convex function, doesn't matter smooth, non-smooth, doesn't matter. For a smooth, of course, you will need infinitely many. For many piecewise linear things, you will need you can do with finitely many. But as long as you're allowed arbitrary family of affine functions, any convex function can be written as pointwise supremum. Okay, let's try to prove this. So let me state this as a theorem. Let f from omega to r be a convex function with closed epigraph. Okay. So you can guess why this assumption is needed, because eventually we are going to use the basic two theorems that we learned about convex sets. One was the supporting hyperplane theorem, and one was the separation theorem, that if I have a closed convex set and I have a point outside of it, I can draw a separating hyperplane. So closed epigraph is a closed convex set. So those two theorems are very, very valuable whenever you're dealing with convex sets. So they will come over and over again. And by now you have already seen, probably used like 10 times or something. All right, so f be a convex function with closed epigraph, and HAB be a sorry. So let f be a convex function with closed epigraph. Then f x is equal to, so maximum of hx, or rather supremum over hx. So what is h? So where h is an affine underestimator of f. So affine underestimator means h is an affine function and it is less than or equal to f. So what it asserts is that f is in fact equal to supremum of all such affine functions. And that this equality is true at every single point. For example, like if I have this, then I can have a couple of affine underestimators. But here I'm asserting that I will take all affine underestimators, whichever are there below that. Then at each point, I will take supremum of that family. So for example, h of x, so since we have been using vector notation, okay. So h of x is always going to be less than or equal to f of x. So f of x is a fixed real number. So if I take the family hi, then it is bounded above. So definitely a supremum exists for that family. Whatever is that supremum is in fact going to be equal to f of x. So that is the assertion actually. So that's the theorem. So f of x is in fact equal to supremum of h, where h is an affine underestimator of f. Okay, so we'll start with the proof. Okay. So here, as usual, we assumed it's a convex domain, meaning it's a convex set with non-empty interior. Okay. Okay, so the epf, so the epigraph of f is a closed convex set by assumption. It is a convex set by definition. If f is convex, then it is a convex set. But here we have, in fact, it is a closed convex set. All right, so at xfx, so xfx is a boundary point, it belongs to boundary of epf or BD. I think we have been using either notation, boundary of epf. So this is on the graph. So xfx is on the graph of f. So now let HAB be a supporting hyperplane at xfx. So HAB, remember, is like A dot X plus B, where B is the offset and A is the outer normal vector, right? And here we have A is not equal to 0. Typically, that's how we define all these affine hyperplanes, because if A is 0, then yeah, then it's just a singleton. Okay. So yeah, so either it is not feasible or it is sorry, it's not singleton. Either it is empty or it is the whole of Rn. So so we are always assuming A is not equal to 0 for supporting hyperplanes. Now, if we look at AB as a vector, then AB transpose x minus z t is going to be less than equal to 0. So why so? So this I'm saying for all z t belongs to APF. All right, so let's look at the picture pictorially. So we have this convex set. This is epigraph. And then what we have is a boundary point here. Now this is a supporting hyperplane. So that means the epigraph is contained in one side of this. So the supporting hyperplane is given by A dot x is less than equal to B. So this is our definition of HAB, right? A dot x. So it is consisting of all those vectors x, so that A dot x is less than equal to B. Sorry, HAB is equal to B, but HAB minus is all those things such that A dot x is less than equal to B. So here, okay, so my bad. Yeah, sorry. So here actually we have a, so this, the graph is in Rn plus 1, right? Epigraph, APF is a closed convex set of Rn cross R. So I'm using some bad notation here. So earlier B used to be an offset, but here let me call alpha as the offset. And this is the vector. This is A is in Rn and B is in R. So in fact, what I'm asserting is AB is not equal to 0 in Rn plus 1. So think of this as a vector in Rn plus 1 and alpha is the offset. Okay. So this is the vector. Essentially what I'm trying to say is this vector AB times x fx is less than equal to AB zt, because AB zt is in fact so AB x fx. So this is on the boundary. So this actually lies in the affine hyperplane. So I can always find one where whenever zt is in the epigraph, so this is in the epigraph, so AB dot zt actually dominates what happens, because this is a point on the boundary. So the offset is given by this quantity, right? AB dot x fx. If that is not clear, so let me rephrase this. So I think perhaps by bad notation, I raised some confusions. So I have this, I have a point x fx here. So now we are in a higher dimension. Earlier, when we were talking about hyperplanes, we were talking in Rn. Now we are in Rn cross R. So we are in Rn plus 1, which is Rn cross R. So here, when we talk about hyperplanes, essentially we want a vector in Rn plus 1. And that is the one we're dealing here. Here, A is not the normal vector. AB is the normal vector. And then we have some offset alpha that is in R. And this equation is nothing but AB transpose, or if you want to write inner product of AB transpose this column vector. Yeah, so A was a column vector. So AB is the vector we have, A, B, right here. So just think of this as the vector for the hyperplane, the normal vector for the hyperplane. So this times X in general will be something like XY. So Y is again a real number. So this will be equal to B equal to alpha, right? That is the definition of the hyperplane. We know x fx lies on the hyperplane. So in fact, I can replace y with fx. So what we know is AB dot x fx is equal to alpha for whatever offset we have, because x fx lies on this hyperplane. Now, whatever is in here, I can assume that it is on one side of this hyperplane. So when I evaluate A dot B, so A B dot ZT, where ZT belongs to this space, to the epigraph, this must dominate this quantity, the offset, right? That is exactly what it means to be the one of the half spaces. So this is going to be bigger than or equal to AB XFX. And that's precisely what has been written here. X minus Z. Okay, it's written in the other direction, but it doesn't matter. Either you can take one side. So it depends on how the sign of A and B are given. So there I have written less than or equal to, but it is clear that it will lie completely on one side. The inequality will be consistently on one side for all ZT in the epigraph. All right. So I hope the notation is clear now. With that in mind, so essentially writing this out, writing this inner product out, what do we have? We have inner product of A with X minus Z plus B times f of X minus T is always less than or equal to 0. Now what is T? So ZT is in the epigraph. This implies T is bigger than or equal to f of Z. That is the definition of something lying in the epigraph. T is bigger than or equal to fz. So what we will do is define S as T minus fz. So we're like a dummy variable. We're defining a dummy variable. So this equation has now, it looks like A dot X minus Z plus B times f of X minus f of Z. So we are replacing this. So T is equal to S plus fz, right? So minus S. So this is bigger than or equal to 0. So we have replaced with this dummy variable. All right. So this is true for all Z in omega. So this is important to remember. Here we have a convex domain omega, and this is true for all Z. Now assume
So in the previous page,
X
lesser than
belongs to
0.
interior of omega. We know that is non-empty, it's a convex domain. So assume X belongs to interior. So far whatever we have done was just some general things. Like you take any X in this, then we will find this sort of equation. We'll find AB such that this holds. Now assume that X is in the interior.
So
Now if I take S to, so first let S tend to infinity. That is possible, right? Because T is bigger than or equal to fz, but it can be as big as you want as long as it is above fz. So S can be as big as you want. So, and this inequality will still be satisfied. Now I'll send S to infinity. That means this difference, since these are fixed numbers, X and Z are fixed numbers, fx and fz are fixed numbers. So this difference will go to minus infinity. And this is also a fixed number, right? A is fixed, X is fixed, Z is fixed. So if I send to S infinity, I realize that this is in fact going to be negative eventually. So that means
it should be lesser than 0.
This has to be, oh, did I put a, sorry, I think this is a less than equal to sign. I changed the sign when I came from here to you. That's a mistake. So yeah, so as I send S to infinity, this goes to minus infinity, but I have B times that must actually be less than equal to 0. So B must be positive, because if B is negative, if it is strictly negative, then the product as S goes to infinity will actually, the product will become positive, right? And that will dominate it because B is strictly negative. It has some modulus, and this will go to minus infinity. So the product will go to infinity, which means it at some point it will exceed 0 when you're taking the limit. So with this, we conclude that so B times fx minus fz minus S will go to minus infinity if B is less than 0. So hence, B is bigger than equal to 0. So this is something we established. And till here also we have not used the fact that X is an interior of omega. Right here is what we'll be using. So if B is equal to 0, then, so if B is 0, what happens? We are just making the assertion that A dot X minus Z is less than equal to 0. All right. So now this is true for all z, right? This inequality that we have is true for all z in omega. So if x is in the interior, I can choose a ball like this, x is in the center, and all directions are included there. The magnitude does not matter. So if this direction, if a dot x minus z is positive, then a dot z minus x must be negative, right? So if this is true for all z in omega, so taking z in this unit ball, we conclude that a must be equal to 0 vector. Because essentially it is telling you that a dot the whole real, like whole of Rn is equal to 0. Because x dot xi, if you have a plus sign here, then you have a negative vector here in this ball. So if z is here, x is here, z minus x is just this direction. So as I vary my z, if x is in the interior, I am able to get all directions. And for all directions, a dot that direction is equal to 0, projection onto that direction is 0. That is only possible if a is the 0 vector. But b is 0 and a is 0. What does that mean? Then a comma b is 0. But when we started with the separation theorem, we have assumed that this outer normal vector is non-zero. So that must mean that b cannot be 0. So not possible. So that's what we have concluded. So here we have concluded b is bigger than or equal to 0. And then assuming x is in the interior, we have concluded that b cannot be equal to 0. So summarizing this, what we have concluded. So for x belongs to interior of omega, the separating hyperplane has positive offset, a strictly positive offset, if you want to. Okay. So then what I will do is, okay, now I'm going to choose s equals 0 here. And then what do I have? A dot x minus z plus b times fx minus fz is less than equal to 0. Right? Yeah, it's less than equal to 0. So then I move things around. So what do I conclude? This implies b is strictly positive. So I get a b times fz term on the right hand side. I can divide by b. So okay, first I get b times f of z is bigger than equal to, moving the negative terms here. So this is bigger than equal to a inner product with x minus z plus b times f of x. And then since b is strictly positive, I can divide b throughout, and I get 1 over b times the vector a, x minus z plus f of x. All right. And when I plug in, so this is a affine underestimator, right? So affine underestimator says that x fx lies on this affine plane. So what have we done so far? So if you give me a boundary point, what I have found is an affine hyperplane which is underestimating the whole of the function. So this inequality is in fact true for all z in omega. Okay, so at this point we have found the affine underestimator. So in fact, since the way I have defined f, so the way I have so the right hand side, the way I have defined it, it is the supremum of all h. So in particular, and h is an affine underestimator. So in particular, this affine hyperplane. So this affine hyperplane lies in that set. So in fact, what we have shown is if x is in the interior, then the values match up. Then it is achieved as a supremum of all these. Now the problem can happen at boundary points, because then we don't have this direction, right? This proof fails because I don't have all directions. So I cannot do the argument saying that, okay, plus is also there, minus is also there. Then that means this must actually be equal to 0. And then a must be the 0 vector, because it is the projection onto any direction is in fact turning out to be 0. So that means it must be the 0 vector itself. So that argument will fail at the boundary. So here we have to use the separating hyperplane theorem. So now let's say this is some convex set. These are the boundary points. And I'm drawing a picture in one dimension, but you can draw the same picture in higher dimensions also. without any worries. So in here we have proven that if I take all those hyperplanes H, which are affine hyperplane, which are dominated by F, then these values are in fact attained by the supremum. So supremum H at X is equal to F of X for all X in interior of omega. That's what we've proven. This anyway, we already know that is a convex function because it's an arbitrary family of affine function and its supremum is again convex. But what we have shown so far is supremum H at X is in fact equal to F. Now we have to show this at the boundary. Assume that that is not the case. So assume like these are intervals, let's say Rs. So let, if possible, supremum of H at R is strictly less than F of R. So anyway, it has to be less than F of R, but assume that it is strictly less than, it is not equal to. If it is equal to, we are done. So assume this is the case, then the point R, F of R plus supremum H of R divided by 2. Oh, sorry. Let me not do it this way. So then the point R supremum H of R does not belong to the epigraph of F. That's right, because it is less than FR. Whatever is in the epigraph has to be bigger than or equal to FR. So that means I have a separating hyperplane. So now by separating hyperplane theorem, I have something. So let's say this is the maximum that supremum attains. I can separate these out. Theorem that exists H such that first of all, H of X is less than or equal to Fx simply because it is a separating hyperplane. So each of these points is lying below this. It is satisfying those inequality. So it is an affine underestimator that exists an affine underestimator of F such that H of X, H of R is strictly bigger than supremum over all H of R. This is a contradiction, right? Because this set by definition was the set of all affine underestimators. So this particular H was already in there. So how can you even exceed that value? So that leads to a contradiction that this you can actually separate, strongly separate in fact, because this is a closed set and this is a point, so you can strongly separate. And then you have a value which is actually, you have an affine underestimator which takes a value which is bigger than supremum HR. So that should not be possible. So what we have concluded is in fact this is wrong. In fact, it has to be an equality. So in the interior, we actually took all those affine underestimators which match up directly here. And then we said at the edge, we don't have to choose anything. The supremum here itself is attained. So you might wonder, what about at the end point? We could have done the same argument, take a tangent or something like that. But think of the circle, or a semicircle rather, like the lower semicircle. Then this is actually defining a convex set. This epigraph is in fact a closed convex set. Here, in fact, the supporting hyperplanes at these boundary points. Can someone tell me what is the supporting hyperplane at this boundary point?
The tangent.
This point and this point. At let's say 1, 0.
The tangent at that point.
So this is the epigraph. In fact, there is only one choice of a supporting hyperplane. That is this vertical line. So here you cannot really, at the boundary point, you are not allowed to take this, because if you take the vertical line, what is the supremum? Here you have to take infinity. So it is no longer matching with this function, because the supremum of this hyperplane is in fact infinity at this point. So what this theorem is saying, you don't have to look at the endpoints, look at the interior points. Then all these affine lines, you take this, so they have certain values at this point, right? They're intersecting at some point. If you take the supremum, you'll hit this. And then you don't have to consider the supporting hyperplane at the endpoints. All right. So this finishes the proof of the representation of convex functions as pointwise supremum of affine functions. And this is yet another illustration of the power of the supporting hyperplane theorem and the separating hyperplane theorem. All right, so I think we went far too deep into the details, but anyway. Okay, so this is the last thing we'll talk about today, minimization. So supremum already we saw, supremum of an arbitrary family of convex functions is convex. Functions is convex. This is something which we have already seen. Now we'll talk about families of convex functions and their infimum, like parameterized families. So more specifically, let's say xy is in a convex subset of Rn cross Rm. So this omega is a convex subset. And F is convex on omega. And let's say C is some non-empty convex subset of Rm. Subset in Rm. Okay. Now define this function g of x as infimum over all those y's that belong to C. So infimum of this, of the function f of xy. So the function is on omega. So it has been split up into two component parts, x and y. And for each of those, you are taking, like you're taking a non-empty convex set in Rm. And what you're doing is defining infimum of f on that coordinate. Essentially, you're taking some sort of slice. Like for example, if this was r cross r, like you are in 2 dimensions and you have a convex function, then you're taking a slice. You're taking certain, like this direction, let's say the direction y, and you're taking a slice that will again be a convex function. And you're taking the infimum along like all the points here. So anyway, each slice is convex is obvious, but then you're taking infimum of all those convex functions. So you're taking all these in the y plane. So think of a convex function in the z plane. So it's a function on xy. And at each point you're taking a slice, then you have a minimum value. So f of xy, so y is a so it's an interval in this case. Here's this picture. Right. So this is your domain, like some convex set in here, or you can think of whole of Rn plus m. So here C is a non-empty convex set in R. M equals n equals 1 in this case. So essentially you're choosing some interval here. And then what you're doing is taking y in this interval. So for each value of y, essentially you're slicing along this direction. And then you're taking the smallest value, wherever is the infimum. And then you're taking wherever is the infimum, and so on. So for each x, that's what you're doing. G of x. Yeah, sorry, my bad. So here x is fixed and y is varying along this interval. So you're looking here and you're taking the infimum here. So it is traveling like this. And the claim is this G is in fact also a convex function. So first of all, domain of G is all those x in Rn such that there is some y such that xy belongs to domain of f or omega. Otherwise,
can
G
you
is
explain
not
it
defined.
once more?
This infimum will be over an empty set. So it's not really well defined there. So if g of x, so one possibility is that it is always minus infinity. Like for example, f could be declining all the way down. So infimum might be minus infinity. But if g of x is bigger than minus infinity for some x in domain of G, then it will turn out to be g of x is bigger than minus infinity for all x. That's the beautiful thing about the convex functions. All right. And G is in fact convex. The proof is actually like directly again a consequence of Jensen's inequality. Maybe I'll just give a quick outline. So if x1, x2 belong to domain of G, meaning there is some y1, so meaning there is y1 such that xy1 belongs to domain of f, and there is some y2 such that x2 y2 belongs to domain of f. So it's essentially you're doing a projection sort of thing onto the first coordinate or the first half of the coordinate system. So now since f is the infimum, since G is the infimum, that means although infimum may not be attained, but if I add an epsilon term, that will be attained. So in fact, f of x1, y1 is less than equal to g of x1 plus epsilon 1, and f of x2, y2 is less than equal to g of x2 plus epsilon 2. So in a sense, I'm saying given epsilon 1, epsilon 2 bigger than 0, there exists y1, y2 such that this holds. That's because g is the infimum, right? So when I add something to the infimum, then that value must be attained by f. So with this in mind, what do I have? G of theta x1 plus 1 minus theta x2. First of all is by definition infimum over y of theta x1 plus 1 minus theta x2 for any vector y in C. So in particular, it is also true for y1 and y2. So this is less than equal to, since it's an infimum, I can replace it with particular values. So theta x1 plus 1 minus theta x2 and theta y1 plus 1 minus theta y2. I can replace any value of y, so it will be dominated. The infimum will be dominated by that value. So this is the one I have chosen. And this will be exactly the convex hull of x1, y1 and x2, y2. And then here I can use Jensen's inequality. So this is less than equal to theta times f of x1, y1 plus 1 minus theta f of x2, y2. But f of x1, y1 is less than equal to gx1 plus epsilon, right? So this is less than equal to theta gx1 plus 1 minus theta gx2. And actually, instead of choosing epsilon 1, epsilon 2, let me just say epsilon is bigger than 0. So given epsilon bigger than 0, and here it's the same epsilon, doesn't matter. Okay, so when I take theta epsilon plus 1 minus theta epsilon, I have this inequality. And this inequality holds for all epsilon bigger than 0, which implies g of theta x1 plus 1 minus theta x2 is, so it satisfies Jensen's inequality. Hence, it is convex. So please go through this proof. It might look a bit technical, but it is very standard technique in the sense whenever you have an infimum of a family of things, you know that if I perturb it or if I increase the value by epsilon, that value is actually going to be attained somewhere. So if I have a thing decreasing to this infimum may not be attained, but if I take any epsilon, something in between is attained. And using, if for example, infimum were attained, this proof would be trivial. I'll just use Jensen's inequality for f and it will be done. But just because the infimum may not be attained, I need some wiggle room to make this proof work. And why do I consider this function? Of course, I've built a new convex function, and we have been saying we want to build new convex functions from old functions. This will show up in the generalization of the von Neumann minimax theorem. Remember, like when we had y, let's say, was in a part of a convex set, like probabilities. So it was a strategy of one person, like in that game where we had put up one finger or two fingers. So we are playing that game, right? And there is a mixed strategy. So X will be the vector of probabilities for one mixed strategy. And essentially, the infimum over this is like taking, you're trying to minimize your loss. So you're looking at all strategies of Y and you're trying to minimize your loss. But we can also look at another function, which is supremum over X and f of xy. That is maximizing the profit. So there is a general, in this setting, also since affine functions are all like convex, concave, everything. So like using duality theory, like the von Neumann's minimax theorem, then it's just about affine functions. So once we study Lagrange duality and everything, but the general form will involve infimum of such functions and supremum of certain other concave functions. So infimum of this convex function and supremum of a concave function, they will actually, there will be an equality condition there. So that is the most general form of von Neumann's minimax theorem. And the thing we saw in linear programming using duality is a special case of that. So that is why I have described this result. It may look technical, but it will start making sense once we revisit this. As I said, Chekhov's gun, we should always remember that. We're not going to waste our efforts during the lectures into going on like on digressing onto some side topics. All right. So I couldn't finish what I really wanted to. So next class, we'll talk about duality of convex functions. Just like we have duality of sets, you can imagine there is probably a notion of duality of convex functions, because Convex functions are nothing but epigraphs. Epigraphs are nothing but convex sets. So if we have a notion of duality for convex sets, that must translate to a notion of duality for convex functions. So that is known as conjugate function for a convex function. So next class, we will talk about that, look at some examples, and then we will give a economic interpretation of the dual conjugate function. So just like we have been talking about economic interpretation of the dual variables and so on in linear programming, we'll do that. And then straight away move to Lagrange duality. That is our main target. That is like the pinnacle of this course, Lagrange duality. All right, so see you next Tuesday.